here we're continuing the Chapter 11 problem solving session problem sets. So we're going onward to question number 2, where you're asked to predict the major organic product or products from the reactions of each of the following compounds with chromic acid or PCC. Now, in order to get these types of questions right, you need to keep the fundamentals listed in that red box on your right in mind here. So when we are dealing with oxidizing agents, the particular oxidizing agent that you're dealing with is going to have a bearing on what type of product you will yield. In other words, what functional group will be present in the product. So typically, with most oxidizing agents that we will deal with, for example, the oxidizing agents that have chromium in the chromium 6+ oxidation state, they will generally oxidize a primary alcohol all the way to the most oxidized product possible from that, which is a carboxylic acid functional group. A secondary alcohol will be oxidized to a ketone, and a tertiary alcohol, since the alcohol functional group that we begin with in a tertiary alcohol will have 3 direct bonds to carbon, since it's tertiary, and our hydroxy group, that carbon that bears the hydroxy group has no direct bonds to hydrogen to lose, so oxidizing this carbon would require the breakage of a carbon-carbon bond. Carbon-carbon bonds are extremely strong and stable, and so therefore, under typical conditions, we're going to see no reaction if we take a tertiary alcohol and attempt to oxidize it. Now, there are ways, when thinking about oxidation, to take a primary alcohol and rather than oxidizing it fully, which means oxidizing it all the way to the carboxylic acid, to oxidize that primary alcohol group selectively just to an aldehyde, which is less oxidized than a carboxylic acid. So the way you can think of it is that we start with a primary alcohol gets oxidized to an aldehyde, and generally an aldehyde gets further oxidized to a carboxylic acid. So we go from something like ethanol to acetaldehyde, an aldehyde, to acetic acid, a carboxylic acid, by taking our primary alcohol and carrying it all the way through oxidation. Now, if you wanted to stop at the aldehyde product, you would not be able to do that with the majority of these chromium-based reagents or with bleach or other typical oxidizing agents. To stop at the aldehyde product here, what you need to use is PCC or PDC. Pyridinium chlorochromate is PCC. PDC is pyridinium dichlorochromate. And what those are going to do is selectively oxidize the primary alcohol to an aldehyde without allowing the reaction to proceed onward to the carboxylic acid. So that's the advantage that PCC or PDC offer. Otherwise, in terms of how they'll react with a secondary alcohol, it's going to be very similar and analogous to the other oxidizing agents that we'll look at. And similarly with a tertiary alcohol, no reaction regardless of which of the oxidizing agents you use. So let's use the information from this box that we've just summarized to determine the solution to each of these parts of the problem. So for cyclohexanol, I encourage you to always sketch out the structure that you are dealing with. So cyclohexanol, 6-membered ring with our hydroxy group. And we're going to, in part A here, treat that with our chromic acid. And chromic acid is one of the oxidizing agents on the chromium 6. We can abbreviate chromic acid as its formula there, CrO3. And we're dealing here with a secondary alcohol because our carbon atom here is directly bonded to 2 other carbons in addition to the hydroxy group that's there. And so secondary alcohols, following our chart, when oxidized chromium reagents get oxidized to ketones. And so what we need to do here to get this problem correct is replace the hydroxy group with the carbonyl group of a ketone. And this is definitely oxidation because we have increased the number of carbon-oxygen bonds and going from our starting material, which I've got the red trace going on there, to the product here as the laser pointer shows. Then we'll do part B of this problem, oxidizing with PCC. PCC is going to react the same to oxidize a secondary alcohol to a ketone as would our other chromium reagents. So we just need to write the exact same product in here. When you're dealing with a secondary alcohol, there's going to be no difference in the resulting product between using chromic acid or using PCC. Now let's do the next problem and see if we can distinguish between the product that will result from using chromic acid versus PCC. So here we are looking at cyclopentyl methanol. So methanol is our 1-carbon alcohol, CH3OH typically, but in this case, since we put in the cyclopentyl branch, that implies that we need to have a 5-carbon ring directly bonded to our methanol group there. And we call this cyclopentyl as a branch rather than as the main chain of this molecule because remember that the alcohol group takes priority in deciding how to go about naming molecules. It takes priority over other functional groups in determining what your longest carbon chain is. So our longest carbon chain is going to be 1-carbon methanol, and then the cyclopentyl group gets attached there. So this is an example of a primary alcohol. And it's a primary alcohol because we have just one bond connecting our carbon that's part of the alcohol group there in red, highlighted here. Just one carbon-carbon bond there, making it a primary alcohol. So when we oxidize that with our chromic acid, we would expect the oxidation to proceed all the way from the primary alcohol to a carboxylic acid functional group COOH in the product. So to draw our expected product here, we make a 5-membered ring, and then we have our 1-carbon chain coming off of which started off as a primary alcohol, and it's going to get oxidized all the way to a carboxylic acid. And remember, this is our abbreviation for carboxylic acid, COOH. And you could also write that out in greater detail if you wanted by showing the carbonyl group and the hydroxy group. And I'll just put a squiggly line here to indicate where that group connects to the rest of the molecule. Now, if we were, instead of using chromic acid, to apply PCC, use of PCC with a primary alcohol is going to result in the reaction stopping at the aldehyde, much like down here, where we oxidize from the primary alcohol to the aldehyde first. That's what's going to happen here when we react with PCC, and the reaction is going to stall at that point. It's not going to go onward to oxidize further. PCC selectively oxidizes primary alcohols to yield aldehyde products. So let's draw that aldehyde product that we would get out of this reaction, and we can abbreviate that aldehyde group up here as CHO. So CHO is our quick way of abbreviating an aldehyde group, which we could draw out in full detail here as a carbonyl group directly bonded to a hydrogen. So then finally we come down to our third question here. Acetaldehyde. Acetaldehyde is a 2-carbon aldehyde molecule. So I'll go ahead and draw that out. Our 2-carbon aldehyde, CH3CHO. And if we oxidize that with our chromic acid oxidizes aldehydes to carboxylic acids. As we saw down here, aldehyde gets further oxidized to a carboxylic acid. And so 2-carbon aldehyde ultimately becomes a 2-carbon carboxylic acid, acetic acid to be specific here. And then if instead we had used PCC in order to carry out this oxidation, we would actually see in this case that there would be no reaction because PCC does not react with aldehydes. It takes a primary alcohol and it stops at the aldehyde product. That means that aldehydes are not reactive with PCC or PDC. So keep these helpful hints with oxidizing agents in mind as you're thinking about how to predict the product of the variety of oxidation reactions of alcohol.